Okay, so as we're talking today about, so I'm going to talk about telescoping series. I'm going to talk about something called partial fraction decomposition, which sounds really impressive. And it's simpler than it sounds. It's something that you could have actually done in Algebra 2 trig, but it's a process that's not talked about very often. It'll help us integrate a few things. And then I'm going to see if I can do a little bit about integration by parts. So those of you in BC, you're already experts on, I'm sorry, those of you in dual credit are already experts on parts. The rest of you, well, you'll have to learn it. Can you do your homework? I mean, yes, you can do your homework. So when I think about telescoping series, like what I want to imagine here, think about like the old telescopes that would like collapse down, like you put in a pocket, like and you extend it out, right? Like that's the picture I want in your head, that as the series extends out, telescopes out, there is a pattern that happens where the next term will partially cancel out the term that came before it. Okay. Now, so I have one here that is going to telescope. So what I want to do is just write down what happens. So when n is 1, so I'm just going to have 1 minus a half. That's the first term, right? Plus, now n is 2. Now n is 3. And so on. If you see it, the next term partially cancels out the term that came before it. So if we want to try to figure out what the sum of this series is, like sometimes these converge and sometimes they don't. Think converge mean it comes to an answer. I'm going to say the answer is 7 or some value. Sometimes I might say it doesn't converge because it goes to infinity. Okay. So to see what happens, we're going to evaluate the partial sums, the sum through n terms. Okay. So when I think about this nth term, like this nth term is 1 over n minus 1 over n plus 1, but it would actually continue after that. So if I think about adding up, though, the first n of these, what would that equal? So this right here, the part that I just kind of highlighted, would be the summation from n equals 1 to n, right? Like this is really what I'm saying, is to add up the first n of them, whatever n is. What would this box equal? Take a second, tell your neighbor. Don't think of it that way. That'll disguise what's happening. So you're right, but think of the pattern that's going to happen, because you don't want to think of each number. When I add up those first n terms, what are the only pieces left? What are the only parts of that summation that don't cancel out? The first term, 1, is that what you mean? Okay, so the 1 is left. I don't know why I crossed it out. The 1 is left. What else is left? And it's being subtracted. This one? So it's this then. so all I did here was, notice that I changed the index to I, just because it's a little confusing to have n's in multiple places, but it doesn't really change the logic of what we're doing. But so the sum of the n terms would be 1 minus 1 over n, okay? Plus 1. I didn't say the plus 1, but. So, how does this help us decide whether it's going to converge or diverge? And it's this statement right here. The sum of the infinite terms will be the limit of the partial sum. The sum of the infinite terms will be the limit of the partial sum. In other words, it's this. It's the limit as n goes to infinity of what we just wrote down. So for us, if n goes to infinity, and if this is what the sum of the first n things look like, do you notice that the answer then has to be 1? Because this denominator gets big and this piece would go to 0 when you think about the limit. And so that's why we're saying here the answer is 1. Now I wonder if you could have guessed that to start with, right? Like when you think about what's happening, I start with the number 1, and if this list never stops, doesn't everything else cancel out? Right? If there's always another term that's going to cancel out the first bit of that thing I write, then there's always going to be another term that cancels everything out. So every 2 terms, I've now canceled out that whole next piece. Okay? So basically, for telescoping, what we're going to try to do is try to write the sum of n things. The sum of n things, and then take the limit as n goes to infinity of whatever we write. And that answer will be the sum. Okay? Let's see if I think I have an example here for us to try. Oh, we can't do that one yet, because I got to do partial fraction first. Questions on telescoping? Does that feel pretty straightforward? Okay, so next, let's talk about partial fractions. I'm going to rewrite this. Jot down this for me. Now, this is one that we could have done already. Like, you could find this antiderivative. How? U substitution. What's U? X squared minus x minus 6, because its derivative is in the problem, right? It's sitting right there. And it would cancel out. That's super easy. What happens if I do this, though? I broke it. I didn't have to, but I did. So I want to think about a different approach that would even solve something like this. Okay? And here's what it means when we think about partial fraction. So here's the phrase. I'm going to abbreviate it, probably just say partial fraction, just because it's a mouthful to keep saying partial fraction decomposition. Decompose, break apart. So to answer partial fraction decomposition, it really just comes from this thought. I'm just going to take the fraction over off to the side for just a minute. And this is why this is actually an Algebra 2 topic. So here's what partial fraction decomposition is saying. That this original problem is definitely, this denominator could definitely factor, if I put my signs correct. Were you okay? So here's what partial fraction decomposition says. There must have been a fraction that looked like this that was added or subtracted to a fraction that looked like this that could have made that answer. I mean, isn't that reasonable? Like, that if I wanted to make a common denominator, couldn't I multiply over here by x plus 2 and x plus 2 and over here by x minus 3 and x minus 3, and that somehow combining everything together that the numerator becomes 2x minus 1? Now, here is why we want to do this, okay? So, like I said, this question itself is not too difficult. Like, so, I mean, I could put a 2 here and it doesn't change any of this work. But if I'm struggling with this integral and I don't know what to do with it, well, isn't this integral the thing I'm struggling with the same as both of those integrals? Then, if I can find the right a and b. But do you notice that these are actually really simple logarithms? Right? If I can get this to be like a number, like 2, or even like with a 2x, I could deal with that. But, so I can break this apart into things that are easier to find the antiderivative of, and that's our goal. So I'm going to leave it with the 1 for now, just because, so you can compare it to the other method. Okay, so partial fraction decomposition just actually begins with the algebra step that you'd expect. So I'm going to write a times x plus 2 plus b times x minus 3 all over x minus 3 times x plus 2. You okay with that? Again, like this really shouldn't feel like a calculus topic, just common denominators of fractions. Now, I'm trying to solve for a and b, right? I'd like to know what a and b are that's going to make this true, because then I could integrate and that's going to make this easier. Well, just as an observation, if these two fractions are supposed to be equal to each other, and if their denominators are the same, what's the necessary conclusion? The numerators are the same. Like, you could cross multiply if you want and divide both sides by x minus 3 and x plus 2, but you're going to finish with this statement. Okay with that logic? Now, when you're thinking about solving here, it might feel strange that I could get an answer because I wrote 3 kind of variables in this statement. But I actually know a lot more about them than I'm first imagining. Do you notice that because this is an x to the first power, and I'm multiplying a by x plus 2 and b by x minus 3, a and b have to be some number. See that? The only way for this to work, the only way to end up with a 2x minus 1 in that numerator is if like a is 3 and b is 2, right? It has to be constants that are just some integer, probably. It could be a fraction, I guess, but they're not going to be. So here's what we're going to do. Here's how we're going to finish this logic. So 2x minus 1. This is the left side. Multiply this out. Distribute, distribute. Now, there's going to be a couple like terms there, right? There's an AX and a BX. And they're being added together. So isn't it A plus B quantity times X? I'm going to factor an X out of those two pieces. And then I'm going to have an A times a 2, and then a B times a negative 3. And so I'm just going to write 2A minus 3B, and I'm just going to maybe, for emphasis, put that in parentheses here. So A and B are some number. What does A plus B have to equal? Has to be 2. You see that? Like, if the coefficient over here ends up being 2, and there's the X right here, doesn't that have to be the number 2? What does 2A minus 3B have to equal? Negative 1. Do you see now we have a system? Solve it. Figure out A and B. And if you've done it correctly, if you put A and B back here in this original statement I made, and you would make a common denominator and combine it together, you should get where we started. Try it. Work together. Help each other out. Be kind to your neighbor. How we doing? We find A and B. What are they both? They're both 1. Now, that means that this original problem could have started right there, right? Like of 1 over x minus 3 plus 1 over x plus 2. If you make a common denominator here, you should finish then with this. So if I'm trying to integrate something I don't understand that factors in the denominator, I should maybe think partial fraction decomposition. Because then if I do the partial fraction decomposition, I can integrate these pieces, which are a lot easier. Now, I hesitate to say this, but I'm going to do it anyway. Because you can handle it. I think so. We'll see. We'll see then. This statement I just wrote, once I figure out the correct A and B, this statement must be true for what values of x? All values of x is the right answer, right? Isn't that what we're saying here? That this function is the same as the sum of those two functions? For any x value I could imagine, right? They have the same domain. They have, everything's the same. So here's what that means. If I go back here, if this is true for any possible x value, you ready? What if I pick an x value cleverly? Like, I don't know, -2. Like, doesn't this statement have to be true for x to be -2? And if x happens to be -2, this side becomes -5. This is a 0. This is b times -5. b must be 1. What's the other clever value of x to consider? 3, because this will drop out. So 5a equals 5. A equals 1. Way simpler than solving a system, isn't it? If you don't know what I just did, ask your neighbor, and then I'm going to move on. New problem. Here it is. So what we have here is a summation, but when you look at that denominator, Like, that's where I'm starting to see the partial fraction decomposition. But let's suppose I want to find this sum. I want to find the sum, right? There's very few of these that we talk about actually finding the sum for, right? Often we'll talk about it converging, but we don't name the sum. That's a super challenging thing to do. So in this one, though, I'm going to say find the sum. Well, it's either geometric, where I could do a calculation of formula for it, or maybe it's telescoping. Okay, so here's my hint. Here's my hint on every summation question you come across. When you see this and you don't know what to do with it, my hint is just start substituting a couple values so you can kind of see what happens. Now, if you think it might be telescoping, it will be to your advantage to factor this and not combine it back together. Like, so what I mean by that is, if I think about this denominator as n plus 3 times n plus 1, and I think about writing like 1 over, 4 times 2, I'd probably just leave it that way. So I want to try to see the pattern. So then I would maybe substitute in 2, and I'm going to get 1 over something. And then I'm going to substitute in 3, 1 over something. So does this, well, I'm sorry, I zoomed out. I'm saying it telescopes. So there must be a way that this is mostly partially canceling out. But then how does the partial fractions fit in with that? See what you can first do by writing out some series, writing out part of the series, and see if you can see the cancel. So how about this? If you're not seeing the pattern yet, I wonder if we could better see the pattern if we separate it. Did you find it? Okay, it's definitely possible to see it in this form. So some people sometimes do, but some people look at it and go, I don't see it. Or maybe you didn't write enough out yet. So here's then the next thing I want you to try. If you want to better see how this might telescope, what I want you to try to do is to rewrite this as some kind of partial fraction decomposition. Sorry. So if I can take this original summation and write it this way, and then instead of substituting into this summation here with 1 and then 2 and then 3 and then 4, substitute in here 1 and 2 and 3 and 4. It might be easier to see than the fractional pieces that are dropping out. Okay, so try that and see if the pattern looks more obvious now. That's the benefit of thinking of it as telescoping. Negative 1/2 and B is positive 1/2, which means it's this summation that we're after. I just rewrote it, putting the fractions in there and the A and the B. Now here's then a hint as to why it might have been hard to spot that pattern of the cancellation, because there's all these halves in those answers. Well, if you think about what you're about to write, let me actually, I don't know what that marking is over there. Let me put this on a clean. So think about if I would start writing this out. I'm going to substitute in 1. Well, it's really this negative 1/2 times a 1 over 4 plus a 1/2 times 1 over 2. Right? Aren't I going to keep writing these halves here for both of these terms? On every single term is either going to have a 1/2 or a negative 1/2. So here's a simpler thought then. This half can actually be factored out. And so now I have negative 1 over n plus 3 plus 1 over n plus 1. So this is as far as the partial fraction decomposition can take us. So now we have to find the pattern. Now here is why we're going to expect a cancellation to happen. Do you see it? That one of these terms is positive, one of these terms is negative. And as n increases, aren't we eventually going to get to a negative term that's going to cancel out a positive term? So your task now is to think about what is the sum of n of them. So if I say I want to sum up from 1 to n of -1 over n plus 3 times 1 over, I'm sorry, those are i's now. I changed it to I plus 1. And now I'm going to take the limit as n goes to infinity of this whole thing, and that should be our answer. So can you do that? Again, my tip, I think what works best on these is to just start writing them out. Start writing them out until the pattern is super obvious as to what's canceling and what is the leftover pieces. Try it. Do you have final? It's 5 something. I think it's 12. Eventually. No. That's 140. So as you think about this summation here, and you start writing out the pieces to it, which I think I had down here, there's definitely this sum of n things. There are pieces left that should have an n in it. But there's going to be a limit as n goes to infinity, which means these things that still have an n in the denominator that you're left with, is it an n plus 3? Is there an n plus 3 here? Okay, we can write it out. I was just trying to make that quicker. But you're going to get terms that are left, and then there's going to be something with n's in it still here. It doesn't really matter what those are that haven't canceled out still yet through n, because if the limit as n goes to infinity, these are going to be pieces that go to 0. And so you're only going to be left with certain terms here, and you just need to figure out what their sum is, and that's the answer. Basically what that means is after a certain point, everything else is going to cancel out. So that's what you really are looking at here. So the final answer here, so if I would add up forever and ever and ever, like this list, there's only certain numbers that we start with are the only ones that won't cancel out. You basically, that's what you're trying to figure out. Which are the ones that aren't going to cancel out? That's the answer to the summation. And in this case, it's 5/12. Those are going to be the only pieces that don't cancel out. So it's the sum of, I don't know, first several of these. Okay. So if you didn't get that, ask somebody next to you. I think almost every table has the right answer now. Be a little careful with your notation about just like glossing over the fact that there is still a limit here. Like that would be a problem like on an FRQ. It wouldn't be a problem on a multiple choice because you're just kind of going, okay, like those are zeros and you're getting the final answer. Nobody sees your work. So let's take a 5-minute break. We'll come back, talk about the last part of integration. 40 questions. 40 questions. Here we go. So we are going to go back and do 7.3, which some of you know, which means you're now the experts at your table to help them. Yes. Now, so here's why we're doing these couple random topics of partial fraction and integration by parts, which is how you should title your notes here. I am not going to quite do it justice in these 30 minutes we have left, okay? But I'm going to try, which means I'm going to maybe go quick because you're clever and you can keep up. So, you actually don't need to write down what's on the screen, okay? Not yet. I just want you to look at it. Now, we are going to have a chapter 10 test soon. My hope, like we really only have 10.5 to do. 10.5 has some other integration, so we're going to focus on 10.5 like all next week. Okay? So next week is our last week before break. Crazy, right? So quick. No. Well, you can do whatever you want, but I won't be there. So, but my plan right now is to have a practice test for you in my math lab that you can work on, and then to have unlocked the actual test that will probably be due the week we get back, probably the Thursday we get back. So if you don't want to take it over break, you don't have to. You need to do it then those couple days we get back, or you could be able to take it over break. That'll be up to you to decide. So that's where I'm aiming for right now, to try to finish chapter 10. We'll start chapter 11 probably that week after spring break. Chapter 11 should take 2 weeks. It's a lot shorter. You'll think it's a lot easier because it is. And then we'll be on to review for the AP test. That'll be it. So you are in the thick of it right now with the sequences and series and the Taylor stuff and all of those air kinds of things. So integration by parts. Go ahead. Question? Nothing. You get your brain. Yes. No. Here we go. You don't have to write this down. Quick, quick. It's so the extension in chapter 11 is area. It's still area between curves, but it's area between polar curves. So don't write this down. Just look. Again, you got to stay focused here. 25 more minutes. What you see on the screen is what? It's the product rule. First semester, derivative of product. First derivative of the second plus second derivative of the first. Do you notice that I could do that? I could rearrange it. That's all I did, is like move the derivative to the middle. Good with that? That means I could say this. Right, if I think about integral, shouldn't like the integral of this be the same as the integral of this? Like it's antiderivative, like there's the constant that maybe doesn't match, but the antiderivative, that function, generically, yeah, should match. And if we think about what I'm writing then, like the integral of this whole side is the same as the integral of both of those pieces. So when you look at it, you really know what that is. We have talked about, the fundamental theorem was all about the derivative of the integral, right? Going back to the original function. That's the integral of the derivative. What is that? U times V partial credit. There'd actually be a constant there that we don't know. Where's that constant coming from, Ella? Yeah, there could have been a constant there, but the antiderivative would produce a constant, right? So that's why when we did it in the other order, we didn't get a constant, because the derivative would have canceled out, but in this order, it would produce a constant. But I'm not going to write it. The reason I'm not going to write it, and that might seem like a contradiction is that on this side of the equation, do you notice that there's another integral? That integral is also going to produce a plus c, right? So I don't need to put, again, plus c and plus c to just write plus c. So what this last statement is, I'm going to simplify it to mean to write this. So instead of writing dv dx, I'm just going to write dv, assuming that we're talking about a function of x, and then same thing with du. This is the part that should be in your notes. That is integration by parts. It's a formula basically for it. What we really should take away from this is integration by parts is the way to undo the product rule. If you're trying to go backwards from a product rule, if you take the derivative of something, you had to use the product rule, and I'm trying to go backwards to where I started, it's integration by parts. I'm going to look at a couple examples here of it. First easy example is this. You should look at this for 30 seconds or less and go, substitution would never work. Substitution would never work. U equals x is the dummy variable change, doesn't do anything. U equals cosine of x, derivative's not in the problem. You're never going to change dx to du. So here's what we're trying to match. So we're starting with the integral of a u times dv, and I'm trying to then say that the answer should be something like this. So basically, I have to look at this stuff here and decide which parts of it are u and which parts of it are the dv. Which parts of it are corresponding to which function from that product rule effectively. I'll tell you how I know this in a minute, but I know that the answer is u should be x, and cosine of x times dx should be dv. Now first, I'm going to prove that it works, and then we'll see about how I knew that that was the right substitution there to make. So the answer to this question, so the answer to the original problem, x times the cosine of x dx, should be u times v. Okay, well I know what u is, it's x. So u times v. Well, I don't have v, but I could get it. So if I look at this, doesn't this almost look like a separable differential equation from the last unit? Right, when we have separated, we got the v's on one side and then we got the x's on the other. So if I want to solve for v, we should just integrate both sides. So v should be equal to, well, what's the antiderivative of cosine x? I appreciate the fact that you said the plus c, but there is going to be another plus c in a minute, so I'm not going to write the constant. So u times v, so x times the sine of x, minus, so now I'm trying to do this part, minus the integral of v, well I know what v is now, it's sine of x, du. Well, if u is x, what's du? 1 dx, yes. So the integral of x times the cosine of x should be, well, this part's already done, x sine of x, minus antiderivative here, antiderivative of sine of x. So I have negative cosine of x, right? So that would be a plus a cosine of x. And this is definitely producing a constant, plus c. Now, how do we know if we're right? Take the derivative. Now, the derivative of that better be this. Or it doesn't make any sense to call it the antiderivative, right? Because that's what we're saying. It is the antiderivative. So its derivative better be x cosine of x. Do you see our product rule? So first, derivative of the second, plus second, derivative of the first. Derivative of this piece, it's just being added, so I'm going to add actually the derivative of a negative sine of x. Cancel, cancel. You see it gave us the original integrand. Integration by parts. So how did I know that this was the correct substitution? It's this. It's a way to remember it. Lip it is what I say. There would be no way to know, right? So, stands for log, inverse trig, polynomial, exponential, and trig. This side over here, oops, this here is the best choice for you, making this the worst. So basically, we're looking back at these two functions. Like those two functions are related to that product rule. So we're going to look at that list, and that's trying to help us choose the best thing for you. Do you notice the things left on the list you would rather take the derivative of than integrate? Right? Like if I say take the derivative of some inverse trig function, aren't you much happier to do that than if I said find the antiderivative of an inverse trig function? In fact, we don't even know what the antiderivative of the inverse trig function is. If I say find the antiderivative of a logarithm, you actually don't know what that is. Do you know why? It takes this method to find it. So that's the choices for you are the things we're going to take the derivative of. So that's why we're going to make those decisions. So questions on that? Polynomial. So any polynomial function. So think x squared plus whatever. So they definitely could look like this. This is a separable differential equation if you want to think of it that way. You can rearrange it, get all the x stuff on one side, all the y stuff on the other. So I'm going to have something that maybe looks like dy equals 2x e to the minus x dx. Integrate, integrate. Now this side's easy. This is just y. This side is our integration by parts. So I see an integral of something that I'm thinking looks, here's maybe the hint. Do you notice that again, substitution would never work here? The derivative of e to the x is more e to the x things, but it's not an x. The derivative of x stuff is never going to be an exponential. I have two very different functions. That's the clue, it's probably parts. Okay, so according to Lippitt, what's the best choice for you and me? And you, it's 2x. And dv, everything else. Once you choose u, once we choose that, and again, I don't really care where you do with the 2. I think it's best to do what Henry just did and stick it with the x. Just stick it with the first thing it's with. If you bring it out in front, think about what's going to happen. With the integration by parts, you'd have to be careful that you end up distributing this, and people will forget. Okay? So if you stick it with it, you won't. So see if you can finish it. Then I'll show you a tabular method, and then we'll probably be done. Answers on the screen. Who got it right? Bottom answer. If you missed it, can you find your mistake? I would say it's really easy to get a sign mistake on these questions because there's like nested negatives that are going to happen, and so that's a common thing to end up with a plus here between them or something. Any questions on these steps? Anything you don't see? So let me show you same problem, something called a tabular method. The tabular method isn't really a new way to do it. It's actually just an organization, but it makes it super simple. Now it only works if u is the polynomial. So if that's not the case, don't do this method because you won't ever feel like you could get an answer. Okay, it'll just look like it goes on forever. So what we're going to do is we're going to make a table, hence the name tabular method. Amazing. We're going to set u, I'm going to think about u in this column, and I'm going to start with dv in the other. So I'm just going to write 2x, and then I'm going to write e to the negative x. I'm not going to bother writing the dx's or the du's. I'm just going to kind of write this down knowing, okay, I know which one is which. Okay. Now, so on this side, we are going to take the derivative, right? Because that's what happens to the u value. We take the derivative. And I'm going to take the derivative. And it's done. On this side, I'm going to find the antiderivative, right? Because don't we integrate this piece? So I'm going to integrate it, and I'm going to get my minus e to the minus x. Now, notice that right there is v, isn't it? Now, if you look at the work that you had to do on the left, do you notice that we need the antiderivative of that piece again? That's this last piece sitting right here, isn't it? Like there's a 2 here. I'm just going to ignore that for just a second. But there's definitely an antiderivative that has to happen of this piece. Like I'm going to have to find it. So I'm going to do that and write the next antiderivative down. So that should be my e to the minus x. Do you see the answer? U times v, which is right here. If you think about the formula we're writing, we're saying uv minus the integral of v du. So minus is this minus. Do you see that is this piece right here? So if you want to use this method of the tabular, you're actually looking at these diagonal products. The first product, think about it, it's going to have a sign associated of it of a 1, a plus, is what I usually say. We're going to subtract this term, whatever it is. This subtraction comes from the subtraction from the integration by parts right here. Now, if this went on one more step, you would take the next diagonal product, but it would have a plus sign associated with it. You're going to add that term. Now, here's why that should be alternating. Do you see it? If I say uv minus the integral of v du, but if that part, I have to do the step again. Think about what I would write. I'd write uv minus the integral of v du. Do you see that we're going to get an alternating pattern that starts happening? That if this piece takes that step of integration by parts again, I'm just going to nest all these negatives together, and these signs are going to alternate, which means why don't you try tabular method on this problem. It applies because the u is an x squared. You're going to take the derivative until you get a 0. And then you're going to integrate as many as you need so you can get to all the diagonal products. And it's a really clever way to stay organized. You don't have to do this, but if you don't, it gets really, really messy. So try it, and then we're done. I don't know why I didn't write the answer. So we're going to take the derivative. We're going to get a 4x. We're going to get a 4, and then we get a 0. And then over here, we're going to have a minus e to the minus x, now a positive e to the minus x. We're going to get a minus e to the minus x, and a positive e to the minus x. There's our first product. That would be u times v. So the answer to this integral of that dx would be minus 2x squared e to the minus x minus the next diagonal product plus, it's plus a negative, so I'll just change that to a minus 4. And at this moment, you have now run out because that's a 0, but don't forget your constant. Integration by parts. See ya. Have a good night.